Good afternoon, good morning, good evening, depending on the time which you are kindly watching this video. Okay, so our first lesson for today will be physics, which is introductory physics, and the course code is PHY 101. Okay, so I'm going to look at the measurements and units as our chapter one. Right, so in this chapter, we have objectives actually, or things which we need to know, or things which we need to cover. Okay, so we look at the standards of length, mass, and time. We also look at the dimension analysis, the uncertainty in measurements and significant figures. We also look at conversion of units, then estimations and order of magnitude calculations. Right. So first and foremost, I would like to welcome you to the world of physics where we develop theories based on experiments. Right. So our first objective is on the standards of length, mass, and time. Okay. So first we'll look at length. So the standards of length we all know is meter. Then for mass, it's kilogram. Where time, seconds. Okay. Since you know the standard units of length, mass, and time, let's now look at the dimension analysis. Right. So in physics, the word dimension denotes the physical nature of a quantity. For example, the distance between 2 points, where from point 1 to point 2. Right. So this distance now can be measured in different physical. It can be represented in different units. Right. So the same distance can be measured in feet, meters, or furlongs, which are different ways of expressing the dimensions of length. So feet, meters, and furlongs. So these are the dimensions of length. Alright. So now the dimension analysis, it is used to check if dimensions of a quantity in an equation now that those which are added, subtracted, or equated have the same dimensions. Right. So then how do you apply this dimension analysis? How do you use this dimension analysis? So we use dimension analysis to find the correct units of a physical quantity in a formula. Right. So we also use this dimension analysis to guess the correct formula when the units of a physical quantity are known. So there are situations where you find that they have just given you the units and they ask you to guess or to come up with a formula which are supporting those units which you will be given or which you have been given. Or you'll be given a formula, then you check if that formula is correct or if the units are correct. Then this dimension analysis again will be used to check the dimensional consistency of an equation. Right. So there are some equations which are dimensionally incorrect. Then there are also some equations which are dimensionally correct. So look at those equations and how you can do them. Okay. So now uh, let's now look at the symbols we can use to specify the base physical quantities or the basic physical quantities. Right. So dimensionally, we'll express the these base physical quantities using the symbols. Yeah. So for example, the dimensions of length, we use the symbol capital L. Then the dimensions of mass, we use the symbol capital M. Then the dimensions of time, we use the capital T. So now you can ask, why haven't we used other quantities, other physical quantities such as acceleration and everything? Then the other quantities, right? So those are derived quantities, right? So those quantities, they all come from these three basic quantities which I've provided here. Okay, so note that the brackets, these will often be used to denote the dimensions of a physical quantity. For example, they will ask you to give the dimensions of velocity, right? So the dimensions of velocity, write them in form of L over T. So now, where is this L over T coming from, right? So remember, the SI unit of velocity is meters per second, right? So where the meters are dimensions of length with speed, with symbol L. Then seconds is one of the dimensions of what? Time, right? With the symbol T. So first we write the formula for velocity. We say velocity is equal to what? Velocity, sorry, you write the SI units for velocity, which is meters per second. Then those meters per second, those are units of velocity. Then you express them form of dimensions, where you say meters is the dimension of length, then seconds is one of the dimensions of what? Time. Right. So then the dimensions of area A is equal to L squared. Right. So we know that area is equal to length multiplied by length. We just multiply two lengths actually. Okay. Then the dimension of other quantities such as force and energy will be described later. Okay. So now you should take note of the following. Now, so you don't just come up with these dimensions and everything like that, then we proceed to no. So there are rules which you need to follow. And one of the rules we say that quantities that have been added or subtracted must have the same dimensions. So if the quantities have different dimensions, then you can't add or subtract those quantities. You just let them be the way they will be. All right. So then the other one is saying if the terms on the opposite sides of an equation have the same dimensions, then that equation may be correct. If the terms on the opposite side of an equation have the same dimensions, simply means that equation may be correct. For example, we find that right, so in situations where we find that we have okay, so in situations where we find that you have maybe okay, so in situations where you find that you have uh, this thing which is showing here. So on the opposite side you have L over T, and on the other side you also have L over T. Then the given equation, we can conclude that it may be correct. It may be dimensionally correct. Okay, so now let's look at the relationship now. The relationship between acceleration, velocity, and time, as well as distance. Okay, so we have distance x has the dimensions of length, where x is equal to L. Then time t has dimensions t, which is equal to t, and velocity v has the dimensions of length over time. Okay, so say velocity is equal to length over time, and acceleration dimensions has the dimensions of length divided by time squared. So here is the equation. Okay, so notice that the velocity and acceleration have similar dimensions. So these two have similar dimensions except one extra dimension of time in the denominator of acceleration. So we find that for acceleration we have L over t squared. For velocity we only have L over t. Right, so uh, so it follows that v is equal to L over t. Right, so then you have expressions like this one. Okay, so where we have L over t squared multiplied by t. So this can give us the formula which is saying v is equal to a multiplied by t. So the dimension is L over t squared. These are representing what? Acceleration. Then t is representing what? Time. So it might be guessed that velocity equals acceleration multiplied by what? Time. And this is true. Alright, so let's see. So this is the relationship between distance, yeah, the relationship between acceleration, velocity, time, and what? Distance. So this is it. Then let's look at this example where we've been asked to check if the given equation is what? Correct. So now on the rules on dimension analysis, we need to take note of the following. Okay. So when you have been given an equation, or when you're deriving an equation in whichever way, you should take note that the constants or numbers in an equation are dimensionless. So if these constants or numbers, the coefficients actually, are dimensionless, then what will we do to them? We'll ignore them. So when writing the expressions in form of dimension analysis, if we have any coefficients or any constants, we'll ignore them. Right, so now let's check the dimensions of the given equation, this equation which we have been given. Okay, so to make it very simple for you, so step one, now to check the dimensions of this equation. So step one, first and foremost, replace each quantity with its SI unit. So replace each quantity with its SI unit. Right, so we all know that the SI units of velocity is meter per second. Then this is V naught, which is velocity initial. Then the half here, we'll ignore it. Then the units of acceleration, meters per second squared. Then also have units for time, which is seconds, and this time is squared, so we have seconds squared. Okay, so here it is. So we are saying the SI units for velocity meters per second, V naught as well meters per second plus meters per second squared multiplied by second squared. Okay, so we all know where this second squared is coming from. It's coming from this t here. Then the other second squared is coming from the units of acceleration actually, which is meters per second squared. Right. So after I write the units, then step two, you now put the appropriate dimensions for each unit. Okay. So you know the dimensions for length, which is meters. So the dimensions for length, we represent them using the capital L in brackets. Then the dimensions of s, which is second, the dimensions of time, which is second, we represent them using the letter t in these brackets. Right, so now we get So from that equation, right, so where there is acceleration, we put L over T. Then here on the equal sign, I'll put the question mark because this is what I'm trying to prove, to check if this equation is dimensionally correct. Okay, so once I do that, I replace each uh, unit with its dimensions. I'll come up with this thing here. Okay, so you can see that this t squared and t squared will cancel. So these two will kiss each other and disappear. So you remain with something like this. So remember, on the rules, we said we can't add things which have different dimensions, or physical quantities which are the different dimensions. So you can't add the two. Hence, you leave them like this. Okay, so now you compare the two sides. Is the right hand side equal to the left hand side? Probably the answer is no. Hence, the equation is what is wrong. So these are the questions which they'll be asking you. Though some of the questions they are satanic, you will face them. Right. So let's now look at the example. Right. So let's now look at one example. Right. So here it is. So the question is saying determine whether the equation. So we said that we can use dimension analysis to check if the equation is what is correct. Okay. So determine whether the equation distance is equal to velocity multiplied by t squared is dimensionally correct. If not, provide a correct expression up to an overall constant of proportionality. Okay, so you can pause the video and try to answer, then you confirm. Alright, so to check if the equation distance is equal to v t squared is correct, so we'll follow the same procedure. So write the SI unit of each quantity, where x will have meters, v will have meters per second, then t squared will have s squared. Then write in this equation in form of the SI units, we will have m being equal to m over s multiplied by s squared. Now we put the appropriate dimensions for each unit, then we'll come up with something like this. Alright, so this t and t squared, so we'll cancel one t from this t squared, then the other t which is down here, so we remain with lt. So L is equal to lt. So you can see that L, the right hand side is not equal to the left hand side. Okay, so you can observe that the right hand side is not equal to the left hand side. So we can conclude that the equation is dimensionally incorrect. Now, the problem is requiring you to provide a correct expression up to an overall constant of what? Proportionality. So how will you do that? So to make L being equal to L, so the correct equation, so let's now provide the correct equation for the left hand side being equal to the right hand side. So the expression or the dimension should be L is equal to L. So how can you come up with those dimensions? So the equation must be distance is equal to Vt. So you can try to prove if this equation is going to give you L being equal to L, or the dimensions of L being equal to L, then you are well and dry. So this is the part one. Yeah. So this is the part one on measurements and units. So the other part will look at the uncertainty in measurement and significant figures. Also look at the conversion of units, how we can convert units from maybe meters to kilometers and stuff like that. We'll also look at the estimations and order of magnitude of calculation. So these units here, or the contents which are here, they're very much important. Okay, so now see you in the next video. So make sure you like and follow the page actually.